You all need to start by drawing the perfect right triangle, such as I. Marvel at the perfection of my drawing there. Most of this will be reviews. You might have to learn a few new things here, especially the three trig ratios, cosecant, secant, and cotangent. But anyway, hypotenuse, always opposite the right angle. Now normally if you're doing like Pythagorean theorem, these would be called the legs, the two sides that form the right angle. But in terms of right triangle trigonometry, it depends on where the angle is in question. If I put this symbol right down there, theta, then that makes this the opposite. Opposite means across from, and that would make this the adjacent side, just like you learned last year. Adjacent means next to. And the hypotenuse is always opposite the right angle. It's always the longest side. Now, I'm sure you know this, but just so we're clear, I don't always just want to assume things. If I moved theta up here to that corner, this would be opposite. This would be adjacent, but we wouldn't have to move the hypotenuse. The hypotenuse would always stay. Okay? Now, the three trig functions you're all familiar with: sine, theta, cosine, theta, and tangent theta. First of all, these are functions, meaning the angle measure is the input. That's what you put into the function. The output is a ratio of sides of this right triangle. For the sine, it's the opposite length divided by the hypotenuse. For the cosine, it's the adjacent length divided by the hypotenuse. And the tangent is the opposite length divided by the adjacent length. Those are the three. SOHCAHTOA. Yeah, that acronym is pretty popular. There's a couple teachers here at this school that made up their own. SOHCAHTOA, that's those letters, it's just an acronym. S stands for sine, so the sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. Tangent is opposite over adjacent. Here's what they came up with. It's kind of funny. You ready? Some old hippie caught another hippie tripping on apples. Come on, you guys. Apples.
What?
Tripping on apples. Anyway, I don't think that's very school appropriate. We're going to stick with SOHCAHTOA. Some old hippie caught another hippie tripping on apples. Apples.
Apples fell over and
He tripped on an apple.
So another hippie caught him.
What if there was like acid on the road and he like slipped on it, so he tripped? Like, you know, it's not that school trip, right?
We're not going to be able to get around it. It's inappropriate. Here are the remaining three. CSC for short. That stands for cosecant. Okay, and then we have SEC. That stands for Southeastern Conference. No. Stands for the secant. And then we have COT. That stands for cotangent. Now, the reason I've done this in this particular order, the cosecant is very much related to the sine. It's the reciprocal. That's all it is. The cosecant is the reciprocal. So if the sine is opposite over hypotenuse, the cosecant is hypotenuse over opposite. The secant is the reciprocal of the cosine.
So what is the division?
Hypotenuse over adjacent. Cotangent is the adjacent over opposite. Those are the 6 trig functions, or the 6 trigonometric ratios. I mean, here are some basic problems you guys did last year in Algebra 2. Example 1. Ooh, look how perfect these are. Man, I am amazing.
Wait, what was the, how do you say that?
A what?
C1?
Secant? It's cosecant, secant, and cotangent. All right, so we have theta right here. Let's call this 3. Let's call this side 4 square roots of 2. Your task is to find or evaluate the 6 trig functions. Four square roots of 2 is the hypotenuse. So I want you to find sine, cosine, tangent, cosecant, secant, and cotangent for angle theta. Do you notice a problem? We're missing a side. Is that really a problem? Can't we just not ever? I mean, why do we need it? Why do we need this side? Yeah, if we already know 2 sides of a right triangle, we can use quite possibly the most famous theorem of all time, Pythagorean theorem. So let's do a squared plus b squared. If you guys ever have any downtime and you're wondering what you can do, go onto Wikipedia and research Pythagoras. He was a weird guy. Yeah. He really was. I mean, he came up with a great theorem. I'm thankful for that. Thank you, Pythagoras. But he was a weird guy. He founded his own society, or his followers founded this society. That they were called the Pythagoreans. They basically amounted to number worship. I mean, they were just...
It's not on your wall over there.
Yeah, he was strange.
Oh yeah, that's right.
Research it. It's kind of funny. Anyway, which side are we searching for? A, B, or C?
B.
A or B, right? We already know C, so let's say that we're going to search for B. So a squared becomes 3 squared. We don't know b, so that stays b squared. This equals 4 square roots of 2 squared. Now, I can see a lot of mistakes happening here.
16 times 2.
You got to square both of them. You square the 4 and you square the square root of 2. So that becomes 16 times 2. Or you just put them in a calculator. 4 square roots of 2. Close parenthesis, square parenthesis, enter parenthesis.
No, not parentheses.
And it's 32. So that turns out to be 32. Here we have b squared. So b squared, if you subtract 9 on both sides, is 23. And now we have to square root 23. What a fabulous number. All hail Air Jordan, His Majesty. Yeah? Yeah, it could have been A. These two could be A or B. The one that matters is the hypotenuse has to be C. That always has to be C. This one could be A or B. So we have square root 23. That doesn't simplify, so we just leave it alone. So now we can fill the 6 trig ratios. Sine, cosine, and tangent. Let's do those 3 first, because once you find those 3, just flip them upside down, and those will be the other 3. So, the sine. When you all speak at once like that, it's hard to hear.
Square root 23 over plus square root
Oh, okay. Square root 23 over 4 square roots of 2.
I didn't know what you were waiting for.
But we can never have square roots in the...
Or Pythagoras will come back from the dead and slap your face.
Wow.
That's an image I just want.
So we multiply it by the square root of 2 over the square root of 2. And we get the square root of 46 over... Ooh, what is this? 8. Exactly. How does it become 8? Math magic, right? Square root of 2 times square root of 2 is 2. 2 times 4 is 8. But I believe square root of 46. Let's see. What multiplies? It's 2 times 23. That's about it. So that doesn't simplify. We're going to keep it. What's the cosine? Ooh, you already skipped ahead to the end. All right. It's 3 over 4 square roots of 2, but then we rationalize the denominator and get 3 square roots of 2 all over 8. And then the tangent is opposite over adjacent, so it's the square root of 23 over 3. So now we can do this cosecant, the secant, and the cotangent. So the cosecant is the reciprocal of the sine, so it's 8 over square root of 46. And we rationalize. Square root of 46 over the square root of 46. So that's 8 square roots of 46. 4 square roots of 46 all over 23. Now let me make a suggestion to you here. You listening carefully. You don't have to follow it. I would if I were me, or if I were you, or if you were me, or if she were her.
Yes, go on.
Anyway, what is the secant the reciprocal of? The cosine. But do we necessarily have to take this and do the reciprocal of it? I would rather take this one here and do the reciprocal of that. Why this one? It would already be simplified. So do that and don't question it. I'm tired of you guys' questions.
And apparently your father was talking to
Yep. So just reciprocate the first version of cosine and not. I think I just made up a word. Yeah.
It's over to you.
Why is it 8 squared 46?
Say that one more time.
Why is it 8 squared 46? Like, where's
It's this right here, the 8 and the 46 was simplified to 4 over 23. Yeah. And the cotangent is going to be 3 over the square root of 23. Rationalize. Square root of 23 over the square root of 23. So we get 3 square roots of 23 over 23. That is what you can expect from the first section of your homework.
That's not too bad.
I think the only hard part about any of this is having that mindset.
Well, just remember the hippies tripping on apples. And then reciprocate. Here's example 2. A little more thinking question, I guess, for lack of a better word. If the cosine, and they're going to start to use other Greek letters rather than just theta. They're going to use alpha. If the cosine of alpha is equal to 3/4, find the other 5 trig ratios. Essentially, you guys, this is the exact same problem that we just did. We just have to draw our own triangle. And we have to label it accordingly, knowing that the cosine of alpha is 3/4. So, just draw a random right triangle. Now, what information do we have knowing that the cosine is 3/4? We know the adjacent and the hypotenuse. So I'm going to label the hypotenuse with 4. Yeah, choose one of these. Any one of these could be alpha. For example, if I put alpha here, 3 has to be next to it. Yeah? Or if I had put alpha in the other angle, then 3 would have had to be next to that. So essentially the same problem. You guys give a go at it. See how far you can get it.
See? She doesn't
Got an
remember.
opportunity.
Good thing I didn't record all of that.
Did you take it off?
I paused it.
You totally should have put on. Oh. And then I could have showed my mom later.
What do we find for the missing length here?
Yeah, I got a square root of 7.
Square root of 7. Okay. Sine alpha. Cosine alpha. Tangent alpha. All right, we got to speed this up. Sine alpha. What'd you get? Square root of 7 over 4. Cosine alpha, we already knew, was 3/4. Tangent. Square root of 7 over 3. And now we find the cosecant. Secant. That's going to be 4 square roots of 7 over 7. Secant was 4/3. Cotangent is 3 square roots of 7 over 7. Okay. Let's go into the special triangles. So one of them, as mentioned, was the 30, 60, 90 triangle. This is a theorem you guys learned a long time ago in a galaxy far, far away called geometry. But the smallest side of a triangle is across from the smallest angle. You guys remember something about that?
Yes.
So, and I know it might be obvious because of the way it's drawn, but sometimes it's not as obvious. But 30 degrees is the smallest angle, so the side opposite is the smallest side. For the ease of the problems, we're going to call that 1.
2 and 3.
On a 30, 60, 90 triangle, the hypotenuse is double the smallest side. So that's 2. The hypotenuse is 2. And then using Pythagorean theorem, we would be able to find out that the remaining side is the square root of 3. Now the nice thing about triangles and how similarity and proportions work, if I change the smallest side, why can't I change it? If I change the smallest side to a 5, what does that change about everything else? That becomes 10, and that becomes 5 square roots of 3. Okay? Everything's proportional on a 30, 60, 90. The 45, 45, 90 is, well, there we go, an isosceles triangle, meaning 2 of the legs are the same. And again, for ease of solving these problems, we're going to call it 1 and 1. And then using Pythagorean theorem, you'd be able to find that that's the square root of 2. But again, if we enlarge the triangle by some scale factor, if I call this one 6, the other one would be 6, what would the hypotenuse be? 6 square roots of 2. Now what makes these so special, other than how perfectly I've drawn them? Using the special triangles, we can evaluate trigonometric functions without using a calculator. If I asked you to evaluate like the sine of 15, that would have to be done on a calculator. Okay? But if I asked you to evaluate the sine of 30 degrees, that could be done without a calculator. Why? We know the opposite and we know the hypotenuse of an angle that's opposite 30 degrees on a right triangle. So it would be 1/2. Okay, the sine of 30 is equal to 1/2. That we can do without a calculator. And if you're wondering, well, is it really 1/2? Just type in sine of 30. Well, first make sure you're in degree mode. I'm in degree mode. Type in sine of 30, hit enter, is 0.5. So that's the big deal about these special triangles, is you can evaluate trig functions there. So let's practice a little bit of this. Example 12, what are we having on here? 3? Step 3. Evaluate. Ooh, without. A calculator. And I'll be able to tell. You'll have a guilty look on your face if you use the calculator. You won't be able to hide it. Tell me what the cosine of pi thirds plus the sine of pi thirds is equal to. Without using a calculator, you dang cheaters. Now, this question follows our discussion of special right triangles, so it would be safe to assume that we're going to have to use the special right triangle on this problem. Now, I mentioned this, but you might not have heard me. The input into any trig function are angle measures. Pi over 3 is an angle measure. Pi over 3 here is an angle measure. What kind of an angle measure, though? These are radians. These are not degrees. These are radians. Okay? So just change them to degrees. Pi over 3 is 60 degrees. So I'm asking you to do the cosine of 60 plus the sine of 60. So, what is the cosine of 60? One half. Yeah. Cosine is adjacent over hypotenuse. That's 1/2. Hey.
Sorry to interrupt.
I feel like they should like.
Yeah. What's the wrong way then? Receiving chart.
Yeah.
Yeah, how did that happen? That's a cool random button.
Oh my god.
What's the sine of 60? Square root of 3 over 2?
I bet he did random and then moved us. No, he probably moved us and then.
I absolutely did that. Absolutely.
You did?
1/2
The nerve.
plus the square root of 3 over 2 is 1 plus the square root of 3 all over 2.
Wait, I thought the cosine or sine of 30 was what?
The sine of 30 is 1/2.
We're on the side.
But the cosine of 60, if you take a look at this 60-degree angle, that's adjacent over hypotenuse.
So do we use those measurements for all of like the things that don't we're not always using those measurements?
Yep. Anytime you're asked to evaluate without a calculator, you're going to have to assume that you're going to use these special triangles. Question?
How did you get cosine 60?
By referring to this 60-degree angle right here.
So,
Oh,
what's
because you change it from radians to degrees.
but then why did we have the pi over 3?
That's the radian.
Well, pi over 3 is the same as 60. This is radians, this is
Times
degrees.
180 over. Okay.
Yep. Did we talk about, maybe we didn't talk about that. I thought we did. In lesson 7.1, we talked about radians to degrees, right? And degrees to radians?
Yeah.
Okay. Okay, applications. Some of these are just going to be diagrams. Some of them are going to be word problems. So here's a diagram. Oh, there we go. There is. So if we knew that this was a 28-degree angle down there in the corner, and we knew that hypotenuse is 14, and I asked you to solve for x, this is actually the bulk of your assignment. Most of the problems coming from this section include triangle diagrams where you have to solve for a missing side or you have to solve for a missing angle. This is what you can expect for the most part. So, what do we do? Pythagorean theorem, right? If we're missing a side of a right triangle, we just use Pythagorean theorem. But we're missing 2. So Pythagoras, sorry buddy, your theorem doesn't work anymore. Yep. We know this angle. We're trying to find the opposite side from that angle, and we know the hypotenuse. What does that sound like, opposite and hypotenuse? That sounds like sine. So we're going to use sine. So the sine of 28 is equal to x over 14. Now we're not doing a special angle here, so it's assumed you would be using a calculator. Multiply by 14 on both sides. X is equal to 14 times the sine of 28. Doesn't happen very often, but some students get it in their mind that they can multiply the 14 by the 28. And that can't happen. The 28 is inside of the function sine. The 14 must multiply outside of that. So on your calculator, you type in 14 times the sine of 28. 6.6. We'll round to the nearest tenth here. X equals 6.6. Try this one. Hey, they're doing trigonometry over there. Do you hear that?
But they don't.
That's true. That's 51 degrees. The opposite length is 12. I'm asking you to find that one right there. So can we just use sine every single time? We can just use sine probably. Tangent on this one. Tangent of 51. The reason we're choosing tangent, the two sides in question are the opposite and adjacent sides of that known angle right there. So we're going to use tangent. It's not really a problem, but it does complicate things a little bit. X is on the bottom of this ratio. We could do cotangent. You're absolutely right. If we do cotangent, we could do the reciprocal. But now the other problem is, I wouldn't say most, but some calculators don't have a cotangent button. So we can just keep it as tangent. We can multiply by x on both sides. So now we have x times the tangent of 51 is equal to 12.
So x would be 12 divided by the tangent.
Exactly. Divide by tangent of 51. Please don't sneeze in my class. I'm just kidding.
I'll try to hold it in.
Hold it in.
What if I can?
What would happen? Has anybody ever tried to stop a sneeze, like mid-sneeze?
Like mid-sneeze or before the sneeze happens?
Like if you breathe in and you feel it coming, what can you do? I mean, there's nothing you can do.
You probably be like choking that. You can't sneeze.
I have heard that.
Your eyeballs like pop out.
Yeah, your eyeballs.
I don't believe that.
It's
You know, on Mythbusters,
Somebody's eyeballs popped out on Mythbusters.
they do it and they hold open his eyes and it goes like bulge out like that. They have it on the slow
disgusting.
camera. It's gross.
I gotta look.
9.7.
So, Mr.
Yeah.
Just multiply that one both.
Yeah. Yeah, that would have worked. Another example. This is going to be using the application in a slightly different way. Pay attention to the difference. If you don't see the difference, it's going to be hard to know what to do. Here's another triangle. The hypotenuse is 21. This side over here, let's say it's 8. And I'm going to put a big old theta symbol right there. Solve for theta. Find what it means to solve for theta is to find the measure of theta. Now, there are 180 degrees in a triangle. Is it simply a matter of subtracting a couple of angles from 180? Because that's what we did in geometry. You subtracted something from 180, there's the missing angle. The problem is we don't know the other angles. We can't do that. But we do know trigonometry now. And in particular, this angle, that's the adjacent side and that's the hypotenuse. So we know that the cosine of said angle theta is equal to 8 over 21. Now what we're searching for is theta itself. We know the cosine of theta is equal to 8/21, but we don't know theta. It is going to be inverse. Now, I'm not saying you guys, but students who are maybe not as familiar with how functions work, or especially trigonometry, I've heard this suggestion a lot. Well, let's just divide by cosine. Why doesn't that work? Cosine is it has to be cosine of something. You can't just divide by cosine of nothing. Here's another. What's that? Yeah. If the square root of theta was equal to 3, would it make sense to divide by a blank square root on both sides? No. What would you do to the square root? You would do the inverse, which is squaring, right? So in order to get rid of a cosine, we don't divide by it, we do the inverse, which is the notation cosine to the -1. That's the inverse cosine. All of you should have that on your calculator. Inverse cosine.
Is the inverse cosine the same as the secant?
No, that's a good question. No. Now the thing you need to understand about an inverse cosine is it's still a function. Okay, a lot of students try to type it into the calculator this way: 8/21 inverse cosine. What's the problem with this? There's nothing inside the function. You have to type the 8/21 inside of the inverse cosine. So where'd my calculator go? Calculator. There you are. So on my graphing calculator, you have to hit second and then cosine. That pops up with the inverse cosine. That's going to be 8/21. Before I hit enter, the input for a normal trig function is an angle measure. The output is a ratio of side length. When we reverse this and do inverses, the input for an inverse is a ratio of side lengths. So what's the output going to be? An angle measure. The output to whatever I hit here for enter, the output is going to be an angle measure, not a side length. So 67.6. 67.6 what? Degrees, exactly. 67.6 degrees. So